Hi, my name is Noah Zepp. I will be talking to you today about research work I did as a Master of Engineering student under the supervision of Professor Liu and Han Fu at the Flight Systems and Control Lab at the University of Toronto Institute for Aerospace Studies. This work proposes an efficient heuristic for solving a threat prioritization problem that arises in the development of UAV-based autonomous defense systems. To understand this problem, consider the case of a single drone defending a high-value asset against multiple invading drones. With limited range, the defender can only truly pursue one invader at a time. This means the defender must produce a capture order with which the defensive strategy is carried out. Ideally, the strategy should minimize the number of invaders that breach the defense. There is no shortcut to know with absolute certainty from the initial conditions which capture order will defend the asset optimally or not, though we can simulate the outcome of each possible sequence given some predicted invader behavior, and then we can compare the success of the outcome. Thanks to previous work done by my advisor Han Fu, computing the final conditions can be done with ease. If we pick one of the capture order options, make some assumptions, and frame the defense scenario as a differential game, the final conditions of the worst-case scenario can be solved efficiently as a convex optimization problem. To briefly explore how my advisor's method works, we begin by defining some key assumptions. In this case, the defender is assumed to always be faster than any single invader. It is assumed that after the initialization of the game scenario, the agents move at their maximum constant velocities for the remainder of the game. Finally, it is assumed that the invaders will follow their own optimal strategy to reach the protected zone. We define our protected zone as a convex region with a boundary characterized by a constraint placed on a convex function g. This function allows us to represent the strategy of the invader as a minimization of this convex function. Though, because the defender is faster, we can break the playfield into two regions. In the green region, any point can be reached by the defender first. However, in the purple region, the invader can reach any point first. This is called the invader dominant region. The best point from the invader's perspective that could be reached within the limits of the game lies on the boundary of the dominant region. We can then call the point on this boundary that minimizes the function g p star, as is the optimal point that can be reached by the invader. The position of p star is a function of the initial conditions, velocity ratio, and the range at which a defender can disable an invader. This is what's called a single defender, single invader game. We can then apply this concept to solving for the outcome of a multi-invader game by decomposing the whole multi-invader game into a series of smaller single invader scenarios, starting the next scenario off with the final conditions from the previous scenario. We augment the definition of the invader dominant region to account for the time that has passed since the start of the single invader game series. With this, we can now solve for the final conditions of the complete single defender multi-invader game. Applying this method to all possible capture orders and then selecting the best outcome is considered the exact solution to the prioritization problem, because through an exhaustive search we can perfectly find the effective defense strategies. Han Fu's method provides a great and simple framework to implement a solver, but an analytical solution to the multi-invader extension of the problem remains elusive, and so each single invader subproblem is solved with a numerical method. The number of single invader subproblems that we must solve in order to implement the exact solution grows by the function n times n factorial, where n is the number of invaders. This means that the sheer number of subproblems that must be solved quickly becomes an issue as n increases, especially in limited computational environments such as onboard flight computers. This leaves the system vulnerable to being overwhelmed by volume, resulting in sluggish decision-making and ultimately suboptimal performance. Any approximate solution cannot guarantee optimality under all circumstances, but can offer significant improvements in computational speed. Balancing this efficiency with reliability is important for practical implementations of this algorithm. This is an NP-hard problem. That means it is very unlikely that a faster exact solution exists. However, we see that in the exact solution, there are some cases where there are many capture orders that optimize the defense. In other cases, when a defender is more evenly matched, there may only be one or two optimal capture orders out of hundreds or thousands of options. When there are many optimal capture order options, it is much more likely that an approximate solution will yield a result that is also optimal. An approximate solution that meets our reliability goals will need to be able to scale its reliance on approximations to limit the amount of error under more difficult conditions when there are less optimal capture order options. We developed a method for approximating the exact solution that relies on adaptive clustering of invaders. This algorithm reduces the search space when doing so is likely to save computational effort at little expense to optimality. It will adapt automatically to retain more of the exact solution when a higher fidelity solution seems to be needed. The algorithm can be broken into two phases, clustering and substep solving. First, we employ the k-means clustering algorithm to efficiently cluster together invaders based on spatial proximity. Then, the clusters are analyzed to see if the cluster models are suitable. If the intra-cluster distances are too large, k-means is reinitialized to allow for additional clusters in the model. This mechanism scales the level of approximation in response to the initial conditions, without the need to solve any single invader subproblems. Next, we create a virtual invader at the centroid of each cluster. This virtual invader is used to determine the order with which the clusters should be captured. Finally, to generate a single complete capture sequence, the smaller capture order problems within clusters is solved. This approximation eliminates any sequences from the search space that split up members of a cluster, drastically reducing the search space. Furthermore, approximating the cluster behavior with a virtual invader is successful because the optimal strategy of the invader is largely based on position. Thus, the closer together two invaders are, the closer together their capture points will be. Through sets of trials with randomized initial conditions, we can compare how the approximate algorithm works against the exact method, specifically in terms of the number of subproblems that must be solved. If we run the algorithm as described, we see a high degree of reliability, and most cases see an over 80% reduction in search space. The level of reliability seen here could be suitable for many applications, but where reliability is of more concern, we can first validate the output of the system. If it is not optimal, we can reinitialize the whole algorithm and force the least correlated cluster to separate. This method will guarantee optimality, but comes at the caveat of potentially taking longer to solve than the exact solution. We did in fact see this happen for some cases. However, for the vast majority of trials, the optimal solution is found in far less time than the full solution. It is our hope that this work can help contribute to bridging the gap between theory and practice when it comes to the implementation of autonomous defense systems. Once again, I would like to thank my supervisor, Professor Hugh Liu, and my advisor Han Fu at the FSC Lab, along with the University of Toronto Institute for Aerospace Studies, for supporting me and my research interest throughout the duration of my project. Thank you all for watching and listening. I hope you enjoyed.